Hello, I'm going to talk about wavelet-based Bayesian analysis of GARMAX model. This is for the IEEE International Conference on Automatic Control and Intelligent Systems. I'm Alex C. Gonzaga from University of the Philippines, Manila. In my talk, I'm going to discuss the following: the GARMAX model, which is the baseline model that motivated the development of the GARMAX model, which is the model in this paper, Bayesian estimation, and some simulation results using this proposed estimation procedure. The GARMAX model, or what we call autoregressive moving average with exogenous effect, can be written in time domain as follows, where yt is the output of the two inputs, epsilon sub t, and the exogenous signal x sub t. Now this specializes to the ARMA model when beta is 0. Now we generalize this to what we call the Gegenbauer autoregressive moving average with exogenous effect, or the GARMAX model, by augmenting the GARMA model using the vector beta xt, where xt is the exogenous variable here and beta is a vector of coefficients. Now this is a general model that specializes to, of course, to ARMAX when d is equal to 0. It is also GARMA, or the generalized autoregressive moving average model, when beta is 0. And of course this when u is equal to 1 or -1, this becomes the fractionally integrated process, and also this includes the autoregressive model and the moving average model, and even the regression model when we only have yt on the left hand side and on the right hand side we only have beta xt. It becomes a regression model. Now the spectral densities of GARMA and the corresponding GARMAX are given here. We have the GARMAX model is just augmented by beta transpose by the spectral density of the exogenous variable x. And if we notice, both GARMA and GARMAX have the same pole at lambda on the interval 0 to pi, where u here is cosine of lambda. So both GARMA and GARMAX have the same poles in their spectral densities, showing that they have the same cyclical component. So an example of a GARMAX spectrum is given by the following. We have here a 3 GARMA model with of course 3 poles at 0.1, 0.3, and 0.45, and the value of the long memory parameters d1, d2, d3 are all equal to 0.3. So this is an example of the spectral density of a 3 GARMA process. Now using empirical data, this one represents the log squared returns of Microsoft stock prices, and we notice that there are poles here. There are actually 7 poles in this graph, and which shows that GARMA is an appropriate model for time series like this. Now in this paper we use the maximum overlap discrete wavelet transform, we take advantage of the properties of this wavelet transform, and the wavelet coefficients are defined by d sub jt. And we notice that in this wavelet coefficient there's no downsampling, which makes it a redundant transform, and because of that it can be efficient in estimating parameters of the model. And aside from that, when the filter length is long enough, then these wavelet coefficients are approximately independent for different levels j. So at different levels we can assume these wavelet coefficients to be uncorrelated, or under normal conditions independent at different levels. And that properties are used in the succeeding discussion of the procedure in Bayesian estimation that we are going to implement. So because of the computational complexity of the exact likelihood function of GARMAX, which is really computationally expensive when used in Bayesian estimation, we used instead the wavelet periodogram using an approximate wavelet Whittle likelihood function. So we defined the wavelet periodogram as follows, which is an alternative to the classical periodogram, but in this case we use wavelet transform. So the maximal overlap wavelet coefficients djt are here, and psi of jt represents the wavelet filter in the frequency domain. So this is the squared magnitude of the wavelet coefficients corresponding representing the wavelet periodogram. So we use this in the likelihood function to facilitate the computation of the likelihood. So for each level j, the log likelihood function is given by this, and where S here represents the spectral density of the GARMAX process, and I sub j is the wavelet periodogram at level j. Now we collect all of this to come up with a wavelet-based log likelihood, and by independence of the wavelet coefficients at different levels j, we can write the overall wavelet-based log likelihood in this manner. So it's just the sum of L sub j at these parameters. So in our Bayesian estimation, we consider the following priors. For the exogenous coefficient, we consider for beta, we consider a normal prior centered at beta, and we choose beta to be close to the expected value of beta sub I, and we choose a sigma to be small enough so that the values are concentrated in the middle, in the mean of the distribution. For the long memory parameter, we use a uniform prior on the interval 0.5 to ensure stationarity of the process. And for the frequency parameter, it is from -1 to 1, so that satisfies the property that the pole is in the interval 0 to pi. And for the variance, sigma squared, for the variance, the prior density is half Cauchy from 0 to 5 to ensure that sigma is non-negative and can have heavy tails. So using these priors and the given wavelet-based likelihood function, we implement a Bayesian estimation approach um, by computing the residuals R sub t, um, yt, and we subtract the exogenous variable here. So, and for each iteration of the sampler, candidate values of the parameters beta, d, u, and sigma are proposed from normal distribution centered at the current values while respecting the support constraints as we discussed earlier. And for each candidate, the residual series is updated using R sub t, using these residuals. We simulated a GARMAX series by first simulating realizations of GARMAX with parameters of GARMA, 0.3, D 0.3, U 0.6, beta 0.5, and sigma equals 1. Then we just added an A-around process with the coefficient 0.5 for the exogenous effect. So we have here plus beta xt. Now we did this for different sample sizes, n equals 128, 512, and also 1024. And in the estimation process, we use wavelets MB16 to ensure that the length of the filter is long enough. So in this case, the length is 32. We have seen in the simulation results, I'm only showing you the simulation results for n equals 128. And we see here that the Bayesian wavelet-based estimator performs better. It has smaller bias in estimating beta, in estimating D, and the result is and also in estimating U. No? Well, the result is comparable, at least in estimating U, although it has higher bias in estimating sigma. And that's true not only for a small sample size, but even for larger sample size like 512 and 1024. And if we also look at the posterior density, we can see that the posterior densities for the parameters are all unimodal, and the values are concentrated within the estimated value. And I'm showing you here the posterior density plots for n equals 1024. So, in conclusion, the GARMAX model offers a powerful extension to various time series models, including ARMA, ARMAX, GARMA, and many other models, and accommodating not only long memory and not only cyclical behavior, but also some exogenous influences within the same framework. And the simulation results highlight the method's competitive performance in capturing both the fractional parameter D and the exogenous effect, or the exogenous coefficient beta, with a smaller bias than the classical Whittle approach, particularly for moderate sample size. And we have seen that by leveraging the redundant maximal overlap discrete wavelet transform and the computational efficiency of the Whittle type likelihood, this Bayesian approach dramatically reduces computational complexity compared to exact time likelihood evaluations, making it especially useful for Bayesian inference with larger n, because you have to do it many times. You have to compute the likelihood many times. That's all. Thank you.